Dr. Dirk Grupe is an associate professor and chair of the Department of Physics, Geology, and Engineering Technology at Northern Kentucky University. His research focuses on active galactic nuclei, which are accreting supermassive black holes in the centers of galaxies. Dirk, thank you so much for taking the time today.
Yeah, sure thing. Good evening.
So, to start, could you talk about the image behind you and how it relates to your research?
Yeah, it relates to my research because what you are seeing here is an artist impression of an active galactic nucleus. So what you said is absolutely right. So you have a supermassive black hole, and when we say supermassive black hole, this means masses of millions or billions of solar masses. Uh, you couldn't see a black hole, but in order to see these objects, which are some of the brightest objects in the universe, you need what we call an accretion disk. And what happens in the accretion disk is that matter gets warmed up really, really hot because it gets driven towards the black hole, right? But it cannot fall into the black hole simply because what we call in physics angular momentum conservation. It's like the Earth going around the sun. It never spirals down into the sun, even though the sun, if it would theoretically become a black hole, which it can't, but think about this, it would be still on its orbit because all that defines the orbit is the mass. And in order to do this, you need friction. And the accretion disk is made out of matter that is basically, it is a plasma. So you're basically looking at hydrogen, helium primarily, because that's the most, the most common objects in elements in the universe. And then through friction, you lose angular momentum and you get the matter closer and closer and closer to the black hole. It's basically, when you think about a low Earth orbit satellite, they eventually fall down back on Earth or disintegrate in the atmosphere because they get slower through interaction with the upper atmosphere, and that makes them slower. It lowers the orbit, and then eventually they end back up on Earth, right? And the same thing happens here. Now, the accretion disk has a temperature in the inner part of hundreds of thousands of Kelvin, and that's why we can see them in X-rays. And that's why I got involved in this, because I at some point had a sample that came from an X-ray mission called ROSA. That was a German, US, British mission, and was launched 35 years ago, almost exactly on the day. And actually, when you look in the X-ray skies, most of the objects you observe are active galactic nuclei. Most of the sources out there are active galactic nuclei. So if you want to find AGN, you look in X-rays. And so this makes these sources really, really bright. And this picture in particular was from a press release that came out on one of my sources, where one of my colleagues, we published a paper together, and this was an explanation why this particular source was flaring at the time, which means you can see this bright blob here, which came out and was sent along a small jet that came out of this active galactic nucleus.
So, just kind of thinking about the what makes an active galactic nuclei an active galactic nuclei. Could you talk first about what are black holes, and how do we know a black hole when we see it?
Yes. So black holes are a consequence of Einstein's general theory of relativity, but they are so strange that Einstein didn't believe they would be even existing. What they are, you have a very dense object, and what masses do, they bend space-time. I mean, this is even, the sun bends space-time, the Earth bends space-time, and that basically defines how objects move around. There was a famous expression by John Wheeler who said masses define how space-time warps, and the warpage of space-time defines how orbits move around that particular mass. And that's what we see. I mean, we describe this typically with Newton's laws, but you can do this the same thing in the general theory of relativity. Now, imagine that the mass is getting bigger and bigger and bigger and bigger. At some point, you reach a point where your curvature goes so strong that you basically fall into pretty much infinity. What happens is, when you think about this, this stretching of space, so to speak, you stretch out light to infinity. So light has no energy anymore. It has no way to escape from this black hole. So it is really a perfectly black body that nothing can escape anymore from it. You alluded also to the next question: how do we know these things even exist, right? I mean, that was Einstein's problem, because black holes are strange, right? Because they isolate themselves totally from the rest of the universe. Um, they are, in a matter of fact, actually the simplest objects in the universe, because you can describe a black hole by two things, essentially, by its mass and by its spin, how fast this thing rotates. Theoretically by electric charge, but that's more for theorists. That's not really what we do in astrophysics, because our objects are all neutral. But how do we find them? Well, I said already, if you want to find black holes, supermassive black holes, you look for active galactic nuclei and you look for X-rays because they form an accretion disk, right? So that would be one hint to look for it. The other hint is coming from actually direct observations. Number one is since about 30 years, there are two groups in the world who looked at the galactic center. Our galactic center has a black hole with a mass of 4 million solar masses. So you take the mass of the sun 4 million times. And what they were looking for was the motion of stars in the galactic center. So you can imagine, right? I mean, how do we get the mass of the sun? How do we calculate the mass of the sun? Well, you take Newton's mechanics. And what you measure is the velocity of a planet going around the sun, and you know its distance. Once you have these two parameters, you're done. You know what the mass is. And you can do the same thing in the galactic center now. So what you need to do is you need to look for the motion of stars around the galactic center. The thing is, you have to have a lot of patience, because you need years and years and years of observations in order to do it. Because the one star, the closest one, takes about 15 years to go around that center. So once you have enough orbital parameter, then you can determine what your velocity is, what your distance is, and with that you get the mass. And that's how we know there is a supermassive black hole in the center, because the object is so compact, you cannot come up with something like exotic, like a cluster of, let's say, 2 million neutron stars. That's not going to work, because it would be gravitationally unstable and it would collapse into a black hole anyway. The next thing is what we talked about earlier is the Event Horizon Telescope. What you're doing here is you take radio telescope distributed all around the Earth, and you take a relatively high frequency. And when you observe in this band, then you will be able to create a picture of a black hole. And that has been done with two black holes so far. The first one was in a galaxy called M87, which is about 50 million light years away from us. And then the other one is our galactic center. And you can see exactly what was predicted, theoretically predicted what you would see when you look at this picture. Now, when you look at the pictures, these are not an optical picture. Again, this is a radio picture, but it shows you directly that black holes really exist.
So I also wanted to ask you about quasars. What are quasars and how do they relate to this research?
Quasars and active galactic nuclei essentially are the same thing. You can sometimes astronomers differentiate between the two, because the active galactic nucleus itself is more like the lower luminosity source, while the quasars are really the whopping, the brightest, the most luminous ones. But essentially, you're dealing with the same thing. So black hole, accretion disk, and all the stuff around it. Now, the term quasar goes back to the 1950s, when really bright, whopping radio sources were discovered. And when you have a radio telescope, your spatial resolution isn't that great. When you think about you have a 20-meter dish, then your resolution is right that of the full moon. So there are lots of targets in that area in the sky. So you cannot pin this down to a single source, to an optical source. So you don't know what you're looking at. But radio astronomers were very innovative and created interferometers. So what you are doing now is you take an array of radio telescopes and you put them at a larger distance from each other. And that gives you now the resolution that you need in order to get a position that coincides with an optical counterpart. And that is the same method that was used for the Event Horizon Telescope, right? I mean, you put telescopes together all around the world. You have a very large baseline, and with this baseline, you get that kind of resolution. So what they were doing then, so they could pinpoint it to an optical source. Once you have that, you measure, you get a spectrum, because a spectrum is, so to speak, the fingerprint of an object. So what they found was, well, they found, for example, hydrogen lines, but these hydrogen lines, which hydrogen is the most common element in the universe, so it's easy to find hydrogen lines. So they found those, but they were redshifted. And redshift means that some object is moving away from us. So imagine, you know, you have the police car, you have the fire, the ambulance car moving away from you. So when you hear the sirens coming, approaching you, you hear the blue shift because you hear a brighter tone. And then when the ambulance car passes, you hear this lower tone, which is simply because it is stretched, right? I mean, you stretch the wavelength, and with that, you hear a dialer tone. You have two explanations for this if you observe this with a cosmological or with a source, with an astronomical source. It could be cosmological redshift. So this because the universe is expanding, and we know when an object is further away from us, a galaxy is further away from us, it seems to be moving faster away from us. That would be explanation number one. The problem with that is when it comes to quasars is these things were so bright that in order to explain the luminosity, it would outshine entire galaxies. So when you imagine that our Milky Way has 200 billion stars, and now these centers of galaxies outshines an entire galaxies with 200 billion stars by factors of hundreds or thousands, when you assume that this is cosmological redshift, well, that's, you know, people had no explanation how you can do this. So the easiest explanation is you have a close by object, but then you need to explain the redshift. You could do that if you have a very compact object. Remember when I said, you know, when the object becomes more and more compact, you stretch the space-time continuum more and more. Well, that causes redshift, gravitational redshift. And so if you think about something like a neutron star, so the leftover core of a star, of a massive star that exploded in a supernova, these objects, when you would measure the redshift on the surface of this object, would be the redshift that people measured at that time, which was about 0.3 or something like that. So it was really an explanation. But the problem was that in 1962, an astronomer called Martin Schmidt measured a spectrum of a quasar. At the time, this word was basically developed from quasi-stellar objects because they appear to be quasi-stellar. Because one problem was too is when they pinpoint it to a source in the optical, they couldn't find a galaxy around it because it was so bright that it outshined the galaxy. But what he found was that there are different types of emission lines in that source, and these emission lines had the same redshift. And you cannot have this if this is a compact object like a neutron star, because then they have to be coming from different distances from the neutron star. Otherwise, you cannot explain this. So they would have different redshifts. So it had to be cosmological. So from that point on, we knew these were cosmological objects. And the only way you can really explain it is by an accretion disk. So in the accretion disk, what you do is you convert gravitational energy into radiation. So friction warms up the thing, and then you can see it in X-rays. It makes a black hole the most luminous source pretty much in the universe.
Wow. Well, so you've talked a little bit about the kind of the history of some of this. Can you talk about what has or how has what we know about black holes changed over time?
I would say it has changed dramatically. I mean, even when you look back, something like a decade ago, right? I mean, all these discoveries that I was mentioning before, like the motion of stars around the galactic center, or in particular the Event Horizon Telescope, those were really, really recent discoveries. The first press release probably on the motion of the stars that goes back maybe 25 years ago, something like that. And then when you think about the Event Horizon Telescope, the first press release was in 2019, and then with the Galactic Center in 2022. So that's really, I mean, really, those were breakthrough observations, I would say, definitely.
Yeah. You've also talked a little bit about the technology that is used. Can you talk more about what technology you use both in your work and what technology is used in this type of research generally?
Yeah, I mean, people have, in some ways, have their favorite wavelength range, right? I mean, I did optical astronomy when I started with astrophysics back in the times, my PhD thesis and so on in Göttingen, but I was also involved there with X-ray astronomy, which was basically an evolving field at the time. So what you do in optical astronomy is primarily you look at optical spectra, right? You identify objects by their optical spectra, what kind of lines you see in that spectrum, and then also by the width of the lines, because you can use the width of the lines also to determine the black hole mass, by the way, because these are gases in the vicinity of the black hole that you can use in order to measure the mass of the black hole. So I did that, and then, I got more and more involved with high energy astrophysics because, again, if you want to find supermassive black holes, if you want to find active galactic nuclei, the best way to do this is in X-rays. Now, X-rays are tricky, right? I mean, if I want to do optical observations, and I used this in the past, I went to an observatory like West Texas McDonald Observatory, or I don't know, Kitt Peak, or you go to Chile or someplace, or Hawaii. And so you can do this from the ground. Now, the other one you can do from the ground would be radio. But if it comes to X-rays, anything high energy, anything ultraviolet, high X-rays, gamma rays, you have to go into space, right? And so astronomers have used X-ray satellites since the 1970s, starting with Uhuru, which was a satellite, a small satellite that was launched from the coast of Kenya in 1970. And then that was a breakthrough. And then I would argue probably 20 years later, so 35 years ago, the Rosat mission was another breakthrough because it did an all-sky survey in X-rays for the first time and discovered something like 160,000 sources in the sky. And that's where basically my active galactic nuclei are also coming from. So the majority of the sources that Rosat found were active galactic nuclei. So I use these tools, or have used these tools primarily. These days I'm using the NASA Swift mission. There's my t-shirt. This is actually the one that came out 20 years ago, believe it or not. Swift was launched 20 years ago as a gamma ray burst observatory, but then quickly evolved into an observatory for pretty much anything else. And it's really a unique observatory because Swift really means swift, it's fast, because what it has is there's a telescope that is called the Burst Alert Telescope. Gamma ray bursts, by the way, are the explosions of very massive stars. And when we talk about very massive, we talk about 50, 60 times the mass of our sun. And Swift was launched because we wanted to understand the physics behind these sources much better, because we couldn't before, but with Swift we could. And the idea was, when we detect one of the sources in the sky, Swift would immediately slew from a current observation on a source to the new target within a minute or two. And then we get the data at the earliest time as we can. And we get the data in X-rays as well as in the optical and UV and the ultraviolet at the same time, which is ideal for active galactic nuclei, because one thing that I study is also the variability of active galactic nuclei. But when you do this, you have to make sure that you observe them in X-rays and the ultraviolet at the same time, because otherwise you don't know what you really compare with. So Swift is a big tool for me. The other one, X-ray observatory, is XMM Newton. That's a European mission, as well as NuSTAR. NuSTAR is a mission that goes into hard X-rays, which was launched, interestingly, by a rocket that was dropped from an aircraft. And then
Oh, wow.
they launched it this way in 2012.
Oh, cool.
Yeah.
Well, yeah. So what is the future of this research, and do you see any breakthroughs on the horizon?
I see a couple of things, because when I mentioned earlier that black holes can be described by two things, the mass and the spin. Well, we have the mass pretty much well figured out, right? I mean, if you have anything that moves around the black hole, you can measure the mass. It sounds a little bit too easy. It's of course much more complicated. But the thing is, which makes it more complicated, is the spin of the black hole. And in order to get this, you have to get the X-rays from the really inner part of the black hole, and you have to get to higher energies. There is a line in an ion line that you can study in X-rays, which is relatively bright. And what you're looking is the broadening of the line. And that is caused by gravitational redshift, because these lines are emitted close to the black hole. So what happens if the black hole starts spinning, and that happens because you dump matter on the black hole, and it will spin up the black hole, that also causes that the last stable orbit of the black hole gets closer and closer and closer to the black hole. So if you are able to measure that, you will be able to measure the spin. That has been done with several active galactic nuclei, but it is still very tricky because we don't get much flux in that regime. We don't get many photons in that regime, but there will be a European mission called Athena that should be launched in the mid-1930s, 2030s, of course. And that will probably give us many, many measurements of active galactic nuclei with these broader ion lines from which we can determine the black hole spin. So that is one of the breakthroughs I see. The other one will be from the gravitational wave side, that we can also observe merging black holes. You probably heard about gravitational wave detectors, where it was found that black holes merged. Those were smaller black holes. The first discovery, when the press release came out in 2016, there was a measurement from 2015, where two black holes with masses of 30 solar masses that merged. The other breakthrough in that regime was the prediction of short gamma ray bursts being the mergers of neutron stars. Once you had a gravitational wave signal and you linked this with a signal from in gamma rays that was done by a satellite called Fermi, then you could bring one and one together. So you knew that merging neutron stars cause short gamma ray bursts. Now, what we can do in the future, there is a planned mission that is called LISA, which is enormous. It's in space. It's, there's 3 satellites, millions of kilometers apart, and they will be able to detect the spin of or they will able to see binary black holes rotating around each other. And if these things merge, they will be able to get that signal, which will be, I think, very exciting. But that's, 15 years probably down the road. So we won't see that tomorrow or so. So it's, but there are lots of things which will be very interesting coming up with these new observatories.
Yeah, that's amazing, and that's exciting that we know that there are so many discoveries coming, and yeah. So, Dirk, thank you so much for taking the time to talk to me about your research and share your insights, and I hope we can continue the conversation down the road.
Yeah, hopefully. Well, thank you for having me tonight. That was great.